Boogie woogie woogie. Let's talk about something that gives our world its spark electricity. Now what is it really? Imagine a huge long line of tiny particles called electrons. These electrons are part of atoms, which are the building blocks of everything you see around you. Your chair, your pet, even you. In some materials, like the copper wires inside your walls, these little electrons aren't held on too tightly. They can be nudged along, almost like a massive conga line of super small dancers. When you give them a little push, they start to move from one atom to the next, creating a flow. This flow, this movement of electrons, is what we call an electric current. It's an invisible river of energy just waiting to do some work for us. Think of it like water flowing through a garden hose. If the hose is just sitting there, the water inside isn't doing much. But when you turn on the faucet, you create pressure that pushes the water through the hose. In the world of electricity, a battery or a power plant acts like that faucet. It provides the push, which we call voltage, to get those electrons moving. The higher the voltage, the bigger the push, and the more energy the electric current carries. This is the fundamental idea behind how we power our gadgets. We're just creating a controlled path for these little electrons to follow, and as they move, they carry energy from one place to another. Isn't that electrifying? Now, not all materials let electrons move easily. Materials like copper, gold, and silver are called conductors because they let electricity conduct or flow through them very well. They are the superhighways for electrons. On the other hand, materials like rubber, plastic, and glass are called insulators. They hold onto their electrons very tightly, making it extremely difficult for an electric current to pass through. This is why electrical cords are wrapped in plastic or rubber. The copper wire on the inside carries the electricity, while the rubber coating on the outside keeps it safely contained so it doesn't go where it shouldn't, like into your hand. Safety first, after all. So, when you flip a light switch on the wall, you're completing a circuit. You're basically lowering a drawbridge to let the electron river flow. The switch connects the wires from the power source to the light bulb, creating a complete loop. The electrons start their journey, flowing through the wire, into the light bulb, and back to the source. As they pass through a tiny special wire inside the bulb called a filament, they create so much friction and heat that the filament glows brightly. And just like that, you have light. It's all thanks to the controlled movement of incredibly tiny particles. Science is bright. Alright, let's switch gears to another amazing invisible force, magnetism. You've probably played with magnets before. You know, those cool objects that can stick to your refrigerator or snap together. But how do they work? Every magnet has two ends, a north pole and a south pole. Just like opposites attract in friendship, the north pole of one magnet will always be attracted to the south pole of another. If you try to push two north poles together, you'll feel them push back. They repel each other. It's an invisible force field that you can actually feel with your own hands. It's a fundamental rule of the universe. Opposites attract, and likes repel. This invisible area of influence around a magnet is called a magnetic field. You can't see it with your eyes, but it's definitely there, doing its thing. A great way to visualize this is to sprinkle tiny iron filings on a piece of paper and place a bar magnet underneath. The iron filings will magically arrange themselves into a beautiful pattern of curved lines, arching from the magnet's north pole to its south pole. These lines show you the shape and direction of the magnetic field. The Earth itself is a gigantic magnet, with its own north and south poles, creating a massive magnetic field that protects us from harmful particles from the sun. So, what makes something magnetic? It all comes down to those electrons again, but this time, it's about how they spin. In most materials, the electrons spin in all sorts of random directions, so their tiny magnetic effects cancel each other out. But in certain materials like iron, nickel, and cobalt, you can get all the electrons to line up and spin in the same direction. When that happens, their individual tiny magnetic forces add up to create one big, strong magnetic field. It's like a crowd of people. If everyone is shouting different things, it's just noise. But if they all cheer together, you get a powerful, unified roar. This alignment is what separates a regular piece of iron from a magnet. You can even make your own magnet. If you take a steel paperclip and rub it with a strong magnet, always in the same direction, you can convince the electrons inside the paperclip to line up. After a few dozen strokes, the paperclip itself will become a weak magnet, able to pick up other small metal objects. You've just created order out of chaos on an atomic level, all by using an invisible force. It's not magic, it's the beautiful, predictable science of magnetism at work. Consider the forces. This is where things get really cool. For a long time, people thought electricity and magnetism were two separate, unrelated things. One was about sparks and currents, and the other was about things sticking to your fridge. But it turns out they are two sides of the same coin. They are a dynamic duo, a superpowered team that works together in a phenomenon we call electromagnetism. The connection is simple but profound. A moving electric charge creates a magnetic field. That's it. That's the big secret. When those electrons we talked about are flowing through a wire, they don't just carry energy, they also wrap the wire in an invisible magnetic field. Let's do a thought experiment. Imagine a simple wire connected to a battery. An electric current is flowing through it. If you place a compass near that wire, you'll see something amazing happen. The compass needle, which is just a tiny magnet, will twitch and point in a new direction. It's no longer pointing to the Earth's North Pole. Instead, it's reacting to the brand new magnetic field you just created with your electric current. The stronger the electric current, the stronger the magnetic field will be, and the more the compass needle will move. This discovery showed us that wherever there is electricity in motion, there is also magnetism. They are linked, forever and always. Now hold on, because this relationship is a two-way street. If a moving electric current can make a magnetic field, can a moving magnetic field make an electric current? The answer is a resounding yes. This is a principle called electromagnetic induction. If you take a coil of wire and move a magnet back and forth inside it, the moving magnetic field will push and pull on the electrons in the wire, forcing them to move. And what is a flow of moving electrons? It's an electric current. You can generate electricity just by waving a magnet around. This is the fundamental principle behind how nearly all of our electricity is generated in power plants. Think about it. In a hydroelectric dam, falling water spins a giant wheel called a turbine. This turbine is connected to a generator, which is basically a massive collection of coiled wires and powerful magnets. As the turbine spins, it moves the wires past the magnets, or the magnets past the wires. And this motion generates a huge electric current. So, the heroic team-up of electricity and magnetism isn't just a neat science trick. It's the very engine that powers our modern world. Moving electricity makes magnetism, and moving magnetism makes electricity. It's a beautiful, powerful cycle. We wouldn't know any of this amazing stuff without the work of some brilliant scientific minds. These were people who were incredibly curious about how the world worked and weren't afraid to ask big questions. One of the key players was a Danish physicist named Hans Christian Ørsted. In the year 1820, while giving a lecture, he noticed by accident that the needle of a compass moved whenever he switched on a nearby electric circuit. He was the first person to prove a definite link between electricity and magnetism. It was a real eureka moment that opened up a whole new field of scientific inquiry and set the stage for everything that was to come. Next up on our tour of science heroes is Michael Faraday, an English scientist who was a true experimental genius. Faraday was fascinated by Ørsted's discovery and thought, if electricity can create magnetism, can magnetism create electricity? He spent years trying to figure it out. In 1831, he finally succeeded with his famous experiment involving a magnet and a coil of wire. He showed that by moving a magnet through a coil, he could induce an electric current. This discovery of electromagnetic induction was revolutionary. It gave us the electric generator and the electric motor, two inventions that completely transformed society. Faraday's work laid the practical foundation for using electricity in our world. While Faraday was the master of experiments, James Clerk Maxwell was the master of theory. A Scottish scientist, Maxwell took all the experimental results from Faraday and others and united them into a single, elegant mathematical theory. In the 1860s, he published a set of 4 famous equations, now known as Maxwell's equations. These equations described exactly how electric and magnetic fields are created and how they interact with each other. They are as important to electromagnetism as Newton's laws are to motion. They are the complete rulebook for how electricity and magnetism behave everywhere in the universe. Maxwell's equations did something else incredible. They predicted that these changing electric and magnetic fields could travel through space as a wave, an electromagnetic wave. When Maxwell calculated the speed of these waves, he found that they traveled at the speed of light. This led him to the astonishing conclusion that light itself is an electromagnetic wave. He showed that electricity, magnetism, and light were all different manifestations of the same fundamental phenomenon. His work unified these forces and paved the way for technologies like radio, television, and Wi-Fi. which all rely on sending and receiving electromagnetic waves. So why does all this matter to you? Because the laws of electromagnetism are not just in textbooks. They are at work all around you, every single second of every day. They are the invisible engine running our modern technological world. Let's start with your speakers. How does a speaker turn an electrical signal into the sound of your favorite song? It uses an electromagnet. An electric current representing the music flows into a coil of wire attached to a cone. This coil sits near a permanent magnet. As the electrical signal changes, the electromagnet's field pushes and pulls against the permanent magnet's field, causing the cone to vibrate rapidly back and forth, pushing the air and creating the sound waves you hear. Think about your microwave oven. It uses a device called a magnetron to generate electromagnetic waves, microwaves to be specific. These waves bounce around inside the metal box and are particularly good at shaking up water molecules. When the water molecules in your food get shaken up, they create heat. And that's how your leftovers get warm. It's not magic. It's just a very clever application of electromagnetic waves to heat food from the inside out. Every time you use a microwave, you are using a direct descendant of Maxwell's brilliant theoretical work. It's physics in your kitchen. Even something as simple as a doorbell uses an electromagnet. When a visitor presses the button, they complete an electric circuit. This sends a current through a small electromagnet inside the bell's housing. The electromagnet instantly creates a magnetic field that pulls a small metal hammer, causing it to strike a bell. Ding dong! When the hammer moves, it breaks the circuit, the magnetic field disappears, and a spring pulls the hammer back into place. If the person keeps their finger on the button, this process repeats over and over, creating that familiar ringing sound. It's a simple yet ingenious little machine powered by the fundamental link between electricity and magnetism. From the giant generators in power plants that are built on Faraday's principle of induction, to the tiny electric motors in your phone that make it vibrate, electromagnetism is the unsung hero of our era. The screen you are reading this on works because electricity controls tiny liquid crystals. The internet data that brought this essay to you likely traveled as pulses of light through fiber optic cables or as radio waves through the air, both forms of electromagnetic radiation. Understanding these laws isn't just for scientists. It gives us the power to innovate and build the world we live in. It's a force of nature that we have learned to harness, and it is, quite simply, awesome.